So in the last video, we looked at this principle of finite element analysis where we can break a continuous object into isolated nodes and try to work out the value of, in this case, displacement at those nodes, right? So a natural thing for you to think about is that because we are trying to use this individual point or individual nodes to approximate this continuous function phi x y that describe some irregular shape of the object, you might think, okay, once we know the value of individual point p, x, y, the function phi is basically a sum over, so this should be p, xi, yi. So you might think about, okay, phi is basically a simple summation of all the values at all the nodes inside the object, okay? But this is not true, right? This is the case where we need to introduce a new concept called the shape function. Now, later in the slides or later in the course, we'll be looking at how we actually calculate the shape function. But the idea of shape function is that you can't simply think about an object as individual point being collected together. Right? The reason is because, say, let me grab an object. If you have an object like this and you have, say, one point or one node at this end and the other nodes at that end, right? If you start moving things on one end, because it is a continuous body, it will affect the movement of the other nodes on this particular shape, or in the language of finite element analysis, it will start to affect the movement of all the other nodes on your element, right? So the idea of the shape function is that we somehow need a way to interpolate the movement of all the other points in between two nodes or multiple nodes on the shape, even though we are not calculating the value explicitly at those points, right? So this shape function is basically something that interpolates between the field variables calculated at different nodes. And in this case, we call that n, right? So rather than summing up the value at individual node, you must multiply the field variable at that node with the corresponding shape function, right? So the shape functions basically allow you to interpolate the behavior of your field variable, right? In this case, displacement, at different points of your element or the whole shape, right? Now, generally, this field variable is a bit abstract at the moment, but we'll see later that they are basically some sort of unknown constants that are to be determined when you perform finite element analysis. Now, these functions, they are generally polynomials, right? They are derived to satisfy certain conditions of the node. Basically tells you, okay, for example, if you have a triangular element, right, how does the movement of one node will affect the movement of the other two nodes, right? And this node, this shape function or this interpolation functions can be predetermined, right? Can be predetermined based on your the element of the shape, right? And they are independent. They are variables of the position of your nodes only, right? They are only the function of your coordinates, right? So this function, right, again, describe how change of the field variable at one point will affect all the other points, right? The bottom line is that you are dealing with continuous body, so you can't just sum up the displacement or the field variable at individual nodes, you need to somehow take into account the information of how one movement will affect all the other points in a continuous body. So that's the basic idea of a shape function. Now, this is something called a degrees of freedom, okay? Now, basically, that is governed by how many nodes you are using to describe your object, right? For example, if you have a metal bar and you divide it into 5 nodes, then the degree of freedom is simply 5, right? And if you have 10 nodes, the degree of freedom is basically 10, right? So that's basically determined by this, summation limit at the top, this big N value. Now, of course, if you have higher degree of freedom, that means you divide the object into more nodes. You will have be able to get finer details of how the system responds, right? So the more finite element you are constructing to describe your shape, the more degree of freedom you will have, and of course that will also increase the computational power required to compute the field variables at all the nodes that you have constructed. Right? So now let's just look at the sort of the general procedure of finite element analysis. What are we actually doing by having talked about the principle behind and the idea of shape function? Okay, so typically in a finite element analysis, we will have 3 main steps. Okay, the first step is called pre-processing, right? In that step, you basically define the geometry of the problem, right? You know the shape of the object you try to deal with. You need to decide what kind of element you're going to use. Right? Are we going to use triangle? Are we going to use squares or parallel epiped, so on and so forth? So that's basically also governed by the number of nodes you're going to define, right? How many nodes, how many degree of freedom you want to model this object, right? Typically, you want to start with lower degree of freedom, right? That will give you the answer much quicker because it requires less computational power. And once you have some general idea of, for example, the loading distribution on your shape, okay, some part of the shape might need more points to model them more accurately. In that case, you're putting more nodes at those specific points, right? Once you have this nodal point defined, you also need to understand or put in the parameter of the intrinsic property of the materials. For example, the Young's modulus, right? Those are the intrinsic material parameter that will govern how much the material will deform when you put external loading in, right? You also need to make sure your geometry scale are proportional to the real object you try to model. Right, and then you need to connect all the nodes, right? That's what we mesh up. That's what we call meshing the model, right? Building up all these little elements, right? And finally, you need to understand what are the physical constraints or the boundary conditions that we talked about a few videos ago, right? Where the loading is applied, where are the points where the object is fixed and not allowed to deform, etc., etc. So once you got all this pre-processing done, the computer will actually help you to go through the solution step, right? Basically, the solution is to compute the unknown primary field variables, right? We talked about what are the primary field variables before. Now, in typical cases, there will be the displacement at individual nodes, right? How much the structure will deform, which is computed at each node, right? And once you know the primary field variable, the values of the primary field variables, you can do back substitution. Put these primary field variables back with their value into the equations, and then you can work out the derived variables, such as forces, the stress on individual elements. If you are modeling heat, you can understand how the heat flow, etc. Those are the information or the associated information that we want to know, right? And lastly, there's pre-processing, right? You need to normally in the software that will contain very sophisticated routine help you to show the result, do the visualization, printing the stress strain curve, for example, at certain elements, and which you can get some idea in your practical lab and how these things are sort of put together. So I also attach a few YouTube video which you can watch at your own time before we dive into the mathematical heavy part of the course. So up to now, we discussed some general idea behind finite element analysis. So I hope you can get some sort of high-level understanding of how the whole process is working. In the subsequent part of the lecture, we'll actually look at how you do all this analysis by hand, how you construct the stiffness matrix, how you actually solve the problem. Actually, how you, for example, how you solve this matrix to get the value of the primary field variables, and how do you do back substitution to get forces and stresses, etc. In a very simple example with practically doable by hands. In that case, you can start to get some, a first-hand feeling of how it's done before you actually move on to do it on the computer, right? Because when you do it on computer, it's like a black box, right? The black box hides all the details or all the theory behind. So even though computer give you the right answer, you might not be able to understand, why this answer is like so, how this answer comes from. So that's why we need to work through this procedure by hand with some very simple example to establish your appreciation of this general procedure of finite element analysis.